So the South Pole Ice Core has a couple of main goals. One of those goals is to get like ultra trace gases. And so the reason this is a good site for it is that it has a unique combination of being very cold because it's so far at the pole, yet has a relatively high snowfall. We kind of talk about the ice in three parts. So the upper part is bubbly ice. Bubbles are clearly visible. Then we have a section that we call the brittle ice. So this is where bubbles are still visible, but they're getting smaller and they're under pressure. So when you bring them up to the surface, they want to expand and crack the ice. Now, once you get below a certain depth, those bubbles have actually all diffused out into the ice lattice. So the ice is optically clear.
Most people look at the gas concentration, they want to know how much CO2 is in the bubbles. But you could actually learn a lot just from the physical properties of the bubbles, how many, how they're spaced, how they're elongated, how they're oriented. Like at certain depths, the bubbles cause the ice to be really brittle, and then at certain depths, the bubbles disappear completely and it just becomes clear ice. So kind of like figure out different properties of the ice. Here, the ice is really interesting because it's like flowing from upstream. So normally, you see these layers and they're very, very horizontal across the core, I guess vertical when you're looking at it. But now you're starting to see them and they're tilted a little bit or they're kind of kinked over. It's really cool. So you can kind of get an idea of how much the ice is shearing at that depth.
Our portion, we do the chemistry on the ice core. The primary purpose of that is to date the ice core. So you get seasonal changes in different chemicals in the ice for various reasons. And if you can get samples small enough, you can actually see those changes and then count annual layers going back in time.
The core will contain 50,000 years of climate history, and so that takes us through three big time periods. So the most recent, roughly 10,000 years.
We processed down to 734 meters continuously. And when we stopped at 734, that was about 10,200 years or so. So just about to the end of the Holocene.
That's kind of the stable, warm climate that human civilization has developed in. Between roughly 10,000 and 20,000 years ago was the transition from the last glacial maximum to today. So that's about a 3 to 4 degree C global temperature change. And then the period from kind of 50,000 to 20,000 years is what we call a kind of glacial climate, so much colder than today, though not quite as cold as the last glacial maximum. And it's a period with abrupt climate changes in it.
The primary dating chemical we're using is from sea salt. So we're using sodium and magnesium to get a beautiful signal that shows every annual layer. We pick up volcanic signals using sulfate, and then that sulfuric acid, which also has an annual signal somewhat. You'll see big increases in it for short periods of time. That's a volcano.
We've tied it to volcanoes that we know absolute dates for, and it matches really well. So
we look at ultra trace chemicals. That infers what the dust was, the chemistry of the dust, and how that changes over time, both the amount and the chemistry of it. And from that you can get ideas about wind patterns going back through time.
When we're looking at the multi-track, so we're looking at the stratigraphy of the core, there we're trying to identify any kind of horizontal irregularities. So we can understand if we're seeing each individual year of snow being deposited all the way back for a continuous climate record, or if there may be small little gaps. While we see irregular layers, none are substantial, but we want to understand that process so that we can learn about where to drill cores in the future.
The outside of the core is contaminated. The outside of our stick is also contaminated, though somewhat cleaner. And then we melt it over as a melt head that's even smaller diameter. And then the outside of that goes to waste. The inside, which is now clean, we analyze. But the ends of the sticks are still dirty. So in that freezer, we sit and scrape all the ends before we melt them. And then we actually melt it in a freezer, but it's just like a convenience store freezer, one of those little stand-ups.
I think we were putting 5 cores in the box, 700 meters, divided by 5, it's like 150 boxes or whatever we have to ship back. One wooden pallet fits 8 boxes, and then we put 4 wooden pallets on an Air Force pallet, so that's 32. So we can send 32 boxes on an Air Force pallet, and then one plane can take 2 or 3 Air Force pallets. What's even scary to think about is not how much it weighs, but how much it's worth. That's why we're so careful about every one of those boxes. We put a temperature logger in. We have somebody actually sit on the plane and ride with it back to the station to make sure they keep the plane cold enough. But if you think about how much time and effort and money went into these projects, it's absolutely necessary.
And so this is one way that we can begin to look at not just what the climate changes were, but how they happened. And so it's those kinds of questions that, we're drilling ice cores to help answer so that we can really understand, timescales on decades relevant to human lifetimes and how the climate system interacts and responds, and use these natural climate variations that are big to understand what's going to happen